Now we're going to talk about crystallographic planes. So now you're all experts in directions, which we're going to always notify with either this, so these kind of square brackets for directions, this for family planes, and now we're going to use indices again, and we're going to use planes. So this is for directions and crystallographic equivalent directions, etc., etc., etc. We're also going to have this notation here for planes, and then for families of planes as well. But those are going to come in just a second. So this is for planes. So make sure, again, these for planes, these for directions, these for family of directions, and planes with my squigglies. So now, how do we draw planes? This is going to be a little bit different and probably a little bit less intuitive than that was the case for our directions. So we have to do kind of this procedure and kind of these steps. So when you're drawing planes, first step, we need to find the intercepts. So how does, we need to find our intercepts. Where does our plane intersect our coordinate system? And then so once we find the intercepts, in order to get our HKL, our Miller indices, to figure out our planes, then all we do is we do the inverse. So inverse of intercepts. So let's look at the example of the 1, 1, 1 plane. So let's kind of look at this example here. So this is my 1, 1, 1 plane. So again, HKL. So where does this 1, 1, 1 plane? So first thing, where are my intercepts? So I could say X, Y, Z. Actually, I'm going to do that. I'm going to use this kind of X, Y, Z notation because I want to make clear what are our intercepts and what are our HKL indices. So I could clearly see that this plane is intersecting my kind of X, again, X, Y, Z. My intersection here is at 1. This plane is intersecting X at that 1 direction. So my X-intercept is 1. My Y-intercept here is also 1, right? I'm intersecting my plane right here. And then for my Z-intercept, 1 as well. So second step, we take the inverse. So our H is going to be 1 over X. Our K is going to be 1 over Y. And our L, HKL, is going to be 1 over Z. So our HKL indices is going to be 1, 1, 1. This is our plane. That's kind of the procedure that we're going to be kind of working with and developing here. So again, find the intercepts, then take the inverse of the intercepts, and we're good to go. So that's going to be kind of a straightforward, kind of, a little bit of an easier kind of example that you could kind of experience. Let's say, for example, and you can kind of do the inverse process and draw the plane too. So let's say that you're instead given an inverse problem. So let's say I was given 1, 2, 2 plane. So these are my HKL indices. So H equals 1, K equals 2, L equals 2. All right, well, I know then my x-intercepts are going to be 1 over H, Y equals 1 over K, and Z equals 1 over L. So my x, y indices are 1, 1/2, 1/2. So if I'm drawing my kind of planes here, I use different colors. This is the part where so my plane is going to intersect 1 here. It'll intersect 1/2 here and 1/2 here. So it'll look kind of like this weird, plane like this. But that would be my plane. And you just connect the dots. Awesome. So let's go through another example. Let's look at the case of 1, 0, 0. So let's say, again, we can kind of do that inverse process. Something weird happens here, right? Actually, let's stick on this inverse process. If you're given 1, is it 1, 1, 0? Excuse me. Let's say you're given 1, 1, 0. So I know that my x is going to be 1 over h, that's 1. My y is going to be 1. Uh-oh, what about my z-intercept? What is 1 divided by the reciprocal? What's 1 over 0? It's infinite. How are we going to do an infinity? Well, whenever you see a 0 on the HKL indices, or if you have an intercept that's infinite, this means that that 0 is indicate parallel. So z or an infinite, or that 0 or an infinite value, if you're considering intercepts, that is going to be parallel. So if it's parallel, that means no intersection. So we'll not intersect this axis. Let's take a look at it on the next page. It's kind of easier to kind of look at an example. So let's look on this plane. So what is my x-intercept? Well, I can see here, I'm intersecting at 1 again. What about my y? Where am I intersecting again? And this could kind of go in these other directions. Where am I intersecting my y? Right here. Where is this being intersected at? Never, right? Look at this plane. It's going in this direction. It's never cutting through, if I have I have a plane like this, for example. So let's say, again, that's an ugly, I'm going to redraw this. Let's say I'm over here. I need like a little cube function to automatically pop in there. If I have a plane like this, let's say it's one right here. Let's say this is 1/2. Let's say this is intersecting at a half. Here, I'm only intersecting my z plane, or my L. So the intercept here would be z equals 1/2. But the x and y, am I ever intersecting here? Am I ever intersecting here? No. So x would equal to 0, or again, infinity. Actually, better get infinity. Y is going to be equal to infinite. They're parallel. They're never going to intersect that plane. So here, you can see that it's our z is going to be for the 1, 0, 0. It's going to be infinite. We never cross that z. So our HKL indices are going to be 1, 1, 0. Beautiful, isn't it? Super cool, really nice, kind of a fun exercise. Now, let's look at an even kind of another tricky and tough problem. Let's go ahead and go into here. Let's look, we'll get back to anisotropy, don't worry about it. Ignore this part here. What about this plane? What's kind of unique about this problem? Well, we're intersecting each plane, each xyz at the origin. So I have an intercept at x equals 0 and y equals 0 and v equals 0. So I have a, again, my HKL indices are going to be infinite, infinite, infinite. That's going to be an issue. So whenever you have an intersection, a plane that intersects like the original origin, you have to do procedure. So if we intersect the origin here, we need to redefine and create a new origin. So now I have an origin right here. So now this is my new x or h, this is my new k or y, or actually y or k, and this is my new L or z. So from this origin, and again, you could define your origin here, wherever you want. There's some that are more convenient than others, but you'll kind of see how that works out. So let's go ahead and look at this kind of new origin here. All right, what are we going to do? So let's go ahead and think about this for a second. Looking at this new origin, where are the intercepts? So let's go ahead and define it here. X equals, y equals, z equals. Well, I could see a z-intercept right here very easily. So I see that I have an intercept at z equals 1/2. Excellent. Is there any intersection for x? No, so it's infinite. So you can see there's no plane kind of cutting through this x-axis. What about the y or the k? Well, not in the positive one, but if we go back here, there's an intersection at -1. So writing our HKL indices, the inverse, 0, 1/2, and now what's the inverse of this intercept? 2. So the key thing you want to remember, it's not like in the crystallographic directions, we're not multiplying here, we're taking that inverse. That's the key aspect when you're looking at planes. So we're going to do quite a few different examples. I'll be posting some of our solutions on a problem set with some worked videos, but this is the general procedure that how you want to deal with planes. And it's a beautiful kind of idea, and planes are really very, actually very, very, very important. So actually, we're going to talk about why in just a second. Again, we kind of went through this. Axes are intersected, no parallel planes. It's misleading. Again, you have to basically redefine that origin there. So plane intercepts, again, inverse of the Miller indices, families of planes, curly brackets. So just like we have similar, actually, let's go ahead and look. Just like we said we had crystallographically equivalent directions, we also have crystallographically equivalent planes. For example, let's look at the for 1, 0, 0. How would I draw this plane? Well, it's going to intersect this axis here, so it'd be right here, this front face here. This front face would be my, actually, let me redraw it. 1, 0, 0. And here, what plane is this? Well, let's see, where are we intersecting? This plane is intersecting my y, so it's 1, 0, or 0, 0, 1. If I made a rotation like this, closed your eyes, and I rotated like around this direction, I flipped that cube, could you tell which one was which? Again, assuming that we have the same number of atoms, and again, the plane looks, kind of similar. So that's going to be kind of the key. It's going to differ depending on your different crystal structures, but we're going to get into that in a little bit. No, this is the basic idea. You can't distinguish between if I did that rotation. So we're going to call again these crystallographic equivalent 1, 0, 0. There's also again 1, 1, 0 planes. There's 1, 1, et cetera, et cetera, et cetera. So you can kind of see those different families of planes and those similarities there. Excellent. So before we kind of move on into kind of our discussion of crystallographic structures, one of the things that I kind of wanted to point out is the importance of why are we dealing with these planes? And to give you a sneak peek ahead of what's going to happen, we've been drawing kind of these fairly simple kind of crystallographic structures, these 3D cubic structures. But we're going to find out soon that there are some very, very important planes. For example, right here. This is called a BCC structure. There's going to be some very important planes, for example, this plane. Actually, we'll go ahead and kind of talk through that together. So I'm going to go from here, here, here. It's kind of hard to kind of draw this here, but what is this kind of plane that I'm kind of illustrating here? What's going on here? What type of plane is this? Well, I crossed through my origin, so that's no good. So I'm going to have to do O prime, redraw here, redraw here. I can't scroll down anymore. This is my new X, Y. So what is this plane? Well, I crossed the X, never. So this is the 0, 1 hat, and 1. So this is the 1, 1, 0. You could kind of also draw this like so. The 1, I could also draw it in green here, but I'm going to kind of avoid it because those are crystallographically equivalent. I could draw this plane right here, like that. This plane is very, very important in BCC. Why? Because you can see this plane has the most atoms that go through it. I have an atom like here, 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 and an atom right in the center. This is what's called a closest packed plane. And these directions where, also directions can apply here too. So for example, let's look at, if I were to draw the, in this system, if I were to draw the 1, 1, 1, 1 direction, I would be going through 3 atoms. 3 atoms. So we'd be going through, again, this atom I'm going to draw. Actually, let me draw a different system like this. Here, 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 here at the center. If I was to draw the 1, 1, 1 direction, I would be going through right across that diagonal. So I'd be going through 3 atoms. So these close packed planes or close packed directions where there's more atoms than, say, in this direction, only 2. In that diagonal, we have 3. Those are going to lead to different properties. And when you have properties that vary or change depending on direction or planes, these materials are anisotropic. So material properties will change depending on the different crystallographic directions. One of the best examples that I can give is titanium. So titanium can exhibit either a BCC or an HCP structure. But an HCP structure, and you can look back kind of on, let's see if I can find it on. Oh, I'm so good. You can see for HCP, we have this like A and B axis, but the C axis, our third kind of director, is larger than A and B. Whereas in our cubic system, A equals B equals C. The magnitude are the same. But anyways, let's get back to titanium. So there's a unique property of titanium. If it's in this HCP structure, when you look at the kind of that elongated, I'm going to draw it horribly here. But if you look at that elongated structure, along the C direction, properties like your Young's modulus, capital E, which is a measure of the stiffness of the material, that is going to be, E along the C direction is going to be larger than your Young's modulus along the A or the B direction as well. So the properties will change, and it's a big problem when you're superplastically forming sheets of titanium. They're going to change, and your properties are going to change as well. So it's very important that we understand this and when we process materials or when we stress materials along these different directions or planes, that we understand that the properties change as well. But more into that once we get into kind of our lecture 7, our mechanics lecture. So I will see you all in the next video when we get into finally simple cubic, BCC, and FCC. Can't wait. See you then. Thanks.